Okay, welcome to lecture for section 5.5, the substitution rule for Calculus 1. This is our last lecture for this course, hence my new picture. You've seen me with lots of different hairdos, and this is, I guess, a 3-hair don't. All right, so let's get moving. So what we're going to look at today is the substitution rule, which is a way to undo the chain rule that we saw in derivatives. So as we know, due to the fundamental theorem of calculus, it's important to find antiderivatives in order to solve integral problems. But our antiderivative formulas do not necessarily help us solve derivatives resulting from the application of the chain rule. For example, if we had the integral of 2x times the quantity of the square root of 1 plus x squared, all evaluated with respect to x, dx, we don't really have a method for solving this right now. There's no product rule for integrals, etc., so we can't take the integral of the first times the second, etc. And this is some of the mistakes that students often make, and most of us make, because we're trying to make intuitive leaps. So if I have the product rule with derivatives, maybe I have the product rule with integrals, but I don't have that here. But we can do an interesting substitution. So the anti-chain rule, or the substitution rule is to try to find a function within the integral that when we take its derivative is also in the integral too. And then we can do substitution and maybe solve a simpler integral. Okay, so we're trying to look at these. We have really, if you look at this, we have kind of two functions here, maybe three. We have 2x, that's one function or a term. We have 1 plus x squared, which could be another function or term because it's all within the radical. And then technically we have the radical 2, which you could say is another function. Okay. So one of the things I noticed right away is that the derivative of x squared is 2x. So if I make this my function, 1 plus x squared, then the derivative of 1 plus x squared, the derivative of 1 is 0 plus 2x, so I get this derivative here. Okay? So here I can see that I have a function, 1 plus x squared, and its derivative, 2x, all in the original problem. So let's see how we go about substituting and solving this. Okay? So if we set u equal to our function, 1 plus x squared, then notice the derivative of u with respect to x, just the derivative of this function, is simply 2x. And if we think of the derivative notation again as a fraction or rational expression, if we multiply both sides by 2x, then I get 2x dx is equal to du. Okay? So notice what I'm going to do here is I'm going to substitute in the parts. So we already said that 1 plus x squared is u. 1 plus x squared is u. So I'm going to put the u inside the square root. Notice I also have 2x dx, which we said is equal to du. Okay? So I plug that in, and notice I've taken care of all of the parts. 2x dx, that's du. 1 plus x squared is u. And so I have this really simple integral now, the square root of u, which if I put it into a power form, u to the 1/2, with respect to u, I can simply solve that. Well, my integral is 2/3 u to the 3/2, right? This is my power rule plus c. I substitute back in. I don't leave it here, because remember we want this in terms of x. We want the derivative with respect to x. All I have to do is substitute back in u, which is 1 plus x squared. Okay? Let's check and see if that actually works. So now I can use the chain rule, right? So if I take the derivative of our answer, we should get back to the integral, right? Because this is an antiderivative. So if we take the derivative of our answer, we should get back to our original problem. So taking the derivative of this, we have the chain rule. So I pull the 3/2 down in front. 3/2 times 2/3 is just 1, times the inside function, 1 plus x squared. I subtract 1 from this, so I get 3/2 minus 1 is 1/2. And then I take the integral of the inside, which is simply 2x. The integral of c, since this is a constant, is 0. when I simplify this, I see I get right back to where I started. So this is actually working. So again, the substitution rule here is to simply find a function inside the integrand where its derivative is also inside that integrand, and then do the substitution and have a simpler problem. Okay? I don't really like this notation, but all this is saying is that if we have a composite function, f of g of x, where the derivative is also there, then if we substitute u equals g of x, then we can simply take the derivative, excuse me, the integral of f of u du. Okay? I think it's easier to see in terms of the example than in terms of the definition. Okay? So these are good problems. I've got about 4 or 5 problems coming up. Hit pause, see if you can do them on paper. They're pretty straightforward. Again, all you're doing is you're looking at the integrand, seeing if you can find something to substitute. Again, you have an x cubed here, you have a cosine function, and then you have an x to the 4th plus 2. Do you see a function whose derivative is also one of these functions? Yes, of course. So we have x to the 4th plus 2. That's going to be our u. If we take the derivative of that, we get 4x cubed dx. Again, I've already done the 2 steps there. This is du dx, and then putting the dx over there. So notice if I solve for x cubed dx, because that's what I have here, x cubed dx, right? I don't have a 4 there. I'm going to have to divide both sides by 4. So x cubed dx equals 1/4 du. So this is what I have to substitute in here. Now I can do that when I have a constant, right? Because remember, with integrals and with derivatives, I can pull the constant out in front, the constant multiplier, not a constant sum or a difference, but the constant multiplier I can pull out front. So when I do the substitution here, x cubed dx equals 1/4 du. X cubed dx equals 1/4 du. We saw that there. And then x 4th plus 2 is our u, so we have cosine u times 1/4 du. I can pull the 1/4 out in front and handle that last. And so all I have is the integral of cosine u du. Again, a very simple integral to solve. And so what I have here is 1/4 sine u plus c. And again, substituting the u back in, and I get this function here. If you take the derivative of that, you will get back to our original answer there. Okay? Again, I think it's probably better for you if you take a few minutes and try to solve these on your own. These are also done in the text, so you can see the step through. These are direct examples out of the text. All right. So here it may look like we have something straightforward, but again, we have a function inside of a function. We have the function inside, which is 2x plus 1. The outer function is the square root. So we cannot simply take this integral of this. So if we make the inside function be u, 2x plus 1, notice du is 2dx. Again, all I have is a dx here, so I divide both sides by 2, and I get dx equals 1/2 du. So when I do the substitution, I have to remember that I have that multiplier effect here, 1/2 du. U is 2x plus 1, so I get the square root of u times 1/2 du. I pull the constant multiplier out front again, u to the 1/2 du. Very simple integral to solve, and I get 1/3 times the quantity of 2x plus 1 to the 3/2. Now I'm not going through these. You should be able to solve this kind of integral pretty simply now. It's just the power rule, and then substituting back in the u. Okay? This one can throw students off a little bit because it's a rational expression. But again, notice we have 3 functions. We have an x up top. We have a 1 minus 4x squared in the denominator, but it's also inside of a radical. I can see here that the derivative of 4x squared is going to give me a power of x. So I'm going to set the u equals 1 minus 4x squared because its derivative will be x to the power of 1. So when I set u equals 1 minus 4x squared, I get du equals negative x, 8x dx. All I have is an x dx. I do not have a negative 8, so I need to get rid of this negative 8 by dividing both sides by negative 8. And so I get x dx equals negative 1/8 du. So now I'm ready to do my substitution. All right, my x dx is negative 1/8 du. I'm doing both steps now together in that same part. I'm not taking it slowly now. 1 minus 4x squared is my u, so I get my square root of u in the denominator. Changing this into a power expression so it makes it easier to solve, I get negative 1/8 times the integral of u to the negative 1/2 du. Again, a very simple integral to solve. And when I solve this, I get negative 1/8 times the quantity of 2 times the square root of u. Substitute in back u. Simplify the fraction here. Negative 1/8 times 2 is negative 1/4. And I have my answer. I'm walking through these fast because I'm assuming that once we get to this part, you can solve these. Okay, you should be able to solve these. The big step here is this substitution. Look at all the parts. Does one part set up as the function? When you take the derivative, you have the right power of x there and only constants left. Okay. Here again, we have a composite function, e to the 5x dx. If we set du equal to the exponent, 5x, then du equals 5 dx. Notice again, we don't have a multiplier of 5 here, so we solve for dx and get 1/5 du. Substitute this in, and we get 1/5 e to the 5x dx. Okay, plus c, don't forget your c. Last one here. I think this is the last one, I'm not sure. Example 5. Now, this looks straightforward, right? The integral of tangent x dx. So we actually, no we don't, what am I saying? If we first rewrite this as a ratio of sine x over cosine x, notice now we have two functions, sine and cosine. Well, if I set u equals cosine x, then du, and the reason I do that is so that the dx is going to be in the numerator here instead of the denominator. Then du equals negative sine x dx. Again, I have sine x dx, not negative, so I need to divide both sides by the negative, and so I get negative du. So I can now substitute it in. My cosine x is my u, so that's in my denominator. My sine x dx is negative du, so it's negative 1 out front and the du there. Well, the integral of 1 over u is the natural log of that. We multiply it by a negative. We have cosine x inside plus c. Remember, though, with a logarithm, the multiplier out front can become the exponent. So this is the same thing as 1 over cosine x. So I can simplify this as the log, natural log of the absolute value of secant x. Now, I'd actually would be okay with this answer here, but it's a good idea to remind yourself. Remember with logarithms that if there's a multiplier in front, we can move that to the power, or vice versa. If there's a power here, I can move it to the front. That's the power rule. So the cosine x to the negative 1 is 1 over cosine x, which is secant x, and that's why that's there. Okay. So that was the last kind of evaluation of indefinite integrals. And so what we're going to look now is how do we use the substitution rule for definite integrals. And when we're solving these, there's really two ways to do this. Okay. What we've been doing so far is solving the chain rule integrals all the way back until we have a function of x. So if you have values, limits from a to b that are interpreted in terms of x, all you have to do is substitute those values in at the very end. So again, like the last example, we would just put, I think it was the natural log of secant x. We would just put the values of x in, the value of b minus the value of a, okay, and then evaluate. So here you can see if we're evaluating from 0 to 4 of 2x times the square root of x squared, if we set u equal to x squared, then du equals 2x, so we get the square root of u du. These are still evaluated at x equals 4 and x equals 0. Now notice what I've done here is I've been very explicit here because these are x values, and now we're looking at u values. So I wrote them in as x mainly so I don't forget and solve this here and then plug in 0 and 4. This would be a mistake because notice this is a u value, not an x value. So I have to be very careful here, making sure that I'm plugging in the right values. So what we're saying here, the first way to do this is when you get to the u value, plug in the x value again. Remember, u equals x squared, so I plug that in. I simplify this, and then I solve. And I get 16/3. Okay? Another way I can do this, and this is actually my preferred method, typically, it depends upon how easy it is. When you rewrite the integral in terms of u, you can rewrite the limits in terms of u as well. So here we had u equals x squared, right? Well, notice if u equals x squared and x equals 0, then u equals 0 squared, or 0. When x equals 4, and again, if u equals x squared and x is 4, then 4 squared is 16. So another way I can evaluate this original chain rule integral after I do the substitution is change the limits using my u substitution, in this case u equals x squared, to change the value of the limits. Now as soon as I solve this integral for u, I don't have to go back in and substitute in the x anymore because I have u values here. I have values for u, no longer values for x, because I've done that substitution as well. Then I just simply plug those values in, and you'll notice I get the same answer, which of course I should get. So you can either solve the integral all the way back to x and then plug in your original values, or when you substitute in your u values, change the limits into u's as well. So again, in this case, u is x squared, so if x is 0, 0 squared, 0. If x is 4, 4 squared is 16. Once you do that, you solve the integral for u, and then plug in your limits here because you've changed these to u's as well. Okay? So these are the two different ways to do it. Again, use the original x values, solve till the end and plug these in, solve back to x and then plug them in, or change the limits into u values using whatever substitution formula. So this is not only the end of this lecture, this is the end of the course. Hopefully this has been helpful to you and a great learning experience. Thank you for taking my course, and if you would and feel so inclined, please send me an email with any feedback you have about the course, and also if you'd like, go out and do a Rate My Professor on me as well. Thank you.